Thank you so much. Yeah, I mean, the benefit of being able to ask me questions in this forum is as though there's definitely no chance of me coughing on you while this is happening. But I was really looking forward to being there in person. I love spending time in Copenhagen. And when Jakob told me about all the plans for the festival, I was like, yep, I'm going to be there the whole week. And I cleared my schedule. I had no other work going on. And unfortunately, despite all of that, you can't avoid getting the spicy cough, and I got the spicy cough, and so I'm more or less on the mend now. But so thank you so much for coming along and watching my disembodied head on a screen. Today I'm going to be talking a little bit about words and what they mean and what we often think they mean and how different people have different views about the same words. Now, a lot of the time I sort of talk about uh, boxes and arrows. I spend most of my time looking at system architecture, and we're obsessed by boxes and arrows. It's one of the main things that we focus on. And sometimes we're thinking about the size of those boxes. How big should a box be, or for that matter, how small should a box be? Sometimes we're talking about more interesting things than that, like what should be in a box. And should we break that box up into smaller pieces? A hint, you probably should. Occasionally, we deal with even more important things, like what shape should the boxes be? And of course, I have my own personal views on the shapes of the boxes that you should pick. But often when I'm talking about these boxes and these arrows and the boxes and the arrows and the boxes and the arrows, we often overlook the arrows. And this talk is very much about those arrows, the arrows that we have between the various boxes that we have. When thinking about microservices, which is obviously the area I focus on a fair bit, the arrows are vital in a way. They represent a logical dependency in our architecture diagrams. A microservice architecture only exists because of the interaction between things. In a diagram like this, that arrow is showing one thing depending on another. The returns microservice here needs the shipping service to do something. And this creates some sort of interesting tensions in a world where we want things to be independent. And we can implement those dependencies in lots of different ways, but fundamentally that dependency exists. We depend on this thing. And then a lot of the devil in the detail is around how how that sort of dependency is implemented. And at this point, we start getting into conversations around interactions between services. A lot of the conversation traditionally starts revolving around these two concepts. The idea that we should sort of have a trade-off between synchronous and asynchronous. You've got those people that don't really know about this distinction and just get on with their lives. And then you've got the fans of synchronous programming who often say that if you're doing anything else, you're a bad person. And this talk today is really about these terms, or more really about this term and how this term is absolutely useless. But I'm going to expand upon that and share why. When we get down to it, I've always struggled with those concepts, and for that reason, I've spent a lot of my time thinking instead around two styles of interaction, which I think can often be a little bit easier to define in terms of their pros and their cons, when they're happening and when they're not happening, and are almost separate from the conversation of synchronous and asynchronous. I want to introduce those briefly because we'll come back to these terms throughout the class today. We have the concept of request response, and we have the concept of event-driven interaction. And I think this distinction is a lot more clear cut than the distinction between synchronous and asynchronous. The classic request response based interaction is familiar to many people. And this is often the sort of default interaction model that we fall back to when we first create a service interaction. Because this is an interaction that's so familiar to us, it mimics the idea of a one object calling a method on another object. In this context here, we have a consumer, in this case, the returns microservice, which is sending a request. It's asking for something. And sometimes it could be asking for a piece of data, but more generically, it's just asking for something. It could be asking for some processing to be kicked off. In this particular situation, we've got a microservice which is sort of handling a returns process, and it needs a postage label that it can send back to its customer. The shipping microservice is responsible for working out the most optimum way to ship a product. And based on that, it generates a return label with the courier company of our choice. And that's what comes back as the response. So we have a consumer. This is the thing that consumes a service. We have the request being sent to the shipping service. And hopefully we get a response, and hopefully that response is a happy response. This is very sort of two-way conversational. It's a bit like a telephone call in a way between two parties. And we can compare this with the event-driven interactions, which can feel quite alien and much more passive in a way. In this situation here, we've got the inventory microservice. We've received some new stock into our warehouse, and the inventory microservice, which manages our stock, or at least is aware of what stock we've got, has fired an event to let people know that new stock has arrived. 10,000 copies of Justin Bieber's greatest hits are now in the warehouse. And with event-driven interaction, it's about emitting events, and they're like a fact. You put those facts out there, and it's up for other services in the system to decide if they want to react to that event. And even if they do want to react to that event, it's up to them as to what they do with that information. We're not telling anybody to do anything in this situation. The promotions and the wishlist microservices here, two different microservices could do something totally different with it. The promotions microservice, for example, might automatically apply discounting based on stock levels. The wishlist microservice, though, this might actually alert people that maybe an item of stock that they had back ordered was now available, letting Jakob know that his collector's limited edition box set of Justin Bieber with a holographic front cover is now available for him to order. In this example here, the consumers are on the right side of this interaction. They are consuming the functionality, but they consume the functionality by reacting to it. Whereas with request response, the consumers are the ones that actually initiate the interaction, and that's a subtle difference. So this distinction, I feel, is quite simple and straightforward to me. And most microservice architectures have a mix of these interaction styles. But I wanted you to have these styles at the back of your head, because we're going to go a bit deeper into some of the terms that we use to describe these interactions. And it's really this interaction that I still think is the most commonly described, and yet has the least valuable meanings. So for me, request response event-driven feels concrete. I can point to it and tell you pretty much 99% of the time which one we're talking about. But we traditionally think of sort of the request response based interactions as being either synchronous or asynchronous in nature. Event-driven interactions we would traditionally describe as always being asynchronous. The things reacting to those events are operating on their own threads of execution. Things get a lot murkier in this world, though. And this was the challenge I was coming up with, was when having conversations with people, they'd say, well, I think you should always do asynchronous, or why should I do asynchronous communication? Why is one thing better than the other? And when trying to understand that space, I looked at lots of work done around asynchronous communication, and basically came up with the realization that there is no clear, consistent definition about what asynchronous even means. And this is problematic when it's something that we want to have conversations about constantly. And I was kind of inspired to actually write this talk based on a really great post on his newsletter by Pat Helland. Pat Helland came to the realization that we were using this term eventual consistency. And yet he realized that the problem with the term eventual consistency is that consistency as a word has many different meanings in many different contexts. The concept of consistency in terms of behavior versus consistency in terms of a database transaction versus consistency in the context of eventual consistency, they're all quite different. A little bit of homework for you. Have a think about what you think consistency means for a database transaction, and then actually look up what the definition is of consistency in ACID. And you'll be very surprised as to what it actually means. And so Pat Helen actually made the argument that because eventual consistency was quite different to the other types of consistency we talk about, that he tried to come up with a new name, and he defined it as being eventual convergence. Now, unfortunately for this talk, and this is giving away the lead in a way, I haven't come up with a better name than asynchronous. But at the very least, I want to take you through why I think that term isn't useful. And we'll look at the many different ways in which people interpret what asynchronous means. So while struggling with this, I basically did what I always do, which is try and write down what other people tell me, because it's better for them to be blamed for their opinions than for me. So I put a thing out on Twitter. It's always going to be called Twitter as far as I'm concerned. And I said, what does asynchronous communication mean to you? And I got loads of really interesting responses from an awful lot of people that I've got a lot of time for. And it was so interesting to me that there was very little consensus. So maybe what I found will not shock you, because I've basically given away what I found. One of the first answers I got back was from an old colleague of mine, Darren Hobbs. And Darren Hobbs says that for him, asynchronous communication is the difference between synchronous and asynchronous communication is the difference between sending an email versus having a phone call. And there's a couple of people that had sort of similar responses, that synchronous is more like a phone call and asynchronous is more like email. And at some level, that feels right. But this does imply that asynchronous communication will somehow be slower than synchronous communication. And yet, that doesn't stack up with my own observations in terms of having built a lot of very low latency asynchronous systems. In fact, the vast majority of the low latency computing applications that I've worked in or adjacent to have actually used asynchronous communication mechanisms. So the speed doesn't necessarily line up with that. So that also didn't feel quite right either. But there's something in there. There's a useful distinction in there somewhere. So I started looking at other resources. Some of you, actually, hands up, how many of you have seen the reactive manifesto, seen it or read it? Some of you might even have signed it. It's a useful piece of what I would describe as technical dogma, right? So it's a very opinionated stance on software architecture. And I have no problem with people having strong opinions. I think that's absolutely fine, as long as you back up why. The authors of the Reactive Manifesto put a lot of work into explaining why they think in the way they do and putting some detail around how they think you should build applications. Just to be clear, I agree on some of the stuff in this, and I disagree with a lot of it as well. But I also am friends with a bunch of the authors, so, friends are allowed to disagree with each other. But they have done a nice bit of work to actually define what the term asynchronous means. So this is useful to us, right? These are super smart architects and techies that have built lots of very complicated distributed systems, and they've taken the effort to describe for them what asynchronous means. Fantastic. Here is my grail. I've now got the answer I need. So I can look at this and tell you this is what asynchronous means. So here we go. Asynchronous communication. In the context of this manifesto, we mean that the processing of a request occurs at an arbitrary point in time, sometime after it has been transmitted from client to server. Okay, so the request is processed after it's been transmitted from client to server. So what? Because how would that not be the case ever? As opposed to the server processing the request before I send it, like through some kind of, I don't know, temporal wormhole or something. This is some kind of weird Doctor Who stuff that's going on here. This is kind of already not a very useful distinction. We always send something, process something after it's sent in any situation, otherwise causality does not work. But if we dive a bit deeper into the Reactive Manifesto, they do try, and there are some other clarifications and explanations around these terms. So they say that asynchronous communication is the opposite of synchronous processing, which implies that the client only resumes its own execution once the service has processed the request. So they're saying that synchronous communication, the client cannot continue until the server has processed the request, and then it can continue. So that's kind of a more concrete definition for them of what they mean asynchronous to mean. However, as we'll see really later, there's a better term for what this is than asynchronous. Around the same sort of time, Steve Smith came back and said, for him, when talking about what asynchronous communication meant, he thought that it meant that the TCP connection was going to be open for the duration of the communication. So this is kind of thinking about it from a networking point of view, right? So during a synchronous interchange, I have a connection open, and it has to be kept open for the whole conversation. Now, there's a few kind of devils in the details here, because you've got things like HTTP2, which sends multiple request response streams over a single connection and reuses connections, and some message brokers reuse connections. So this isn't quite right. And so I start poking at Steve. Steve's a friend as well, so I'm allowed to poke at him. I said, Steve, so you're saying if I'm using UDP or Quick, I'm not doing asynchronous? So he clarifies, no, what he actually meant is, I assume you're not blocking for a response. And this is getting a bit more concrete now. And I think this is more concretely what the reactive manifesto is talking about, is client-side non-blocking. So let's explore what that is a little bit and see why it's good and why it may not be the whole thing we need to think about. But non-blocking is at least a better and more concrete term. So let's look at that. Here's a very simple interaction. We've got an enrollment microservice. It's going to kick off some processing. Some stuff's got to happen. And the enrollment microservice needs to go to the loyalty microservice and say, please give this person some points. We need to award Jakob some points because he's signed up to the Justin Bieber fan club. And in addition to awarding him some points, because he's such a big believer, we're also going to upgrade his subscription to Bieber Class 1 Alpha tier, right? So one microservice needing to kind of initiate interaction to other microservices. This would be a classic use of request response in this example here. So I'm going to say one request to loyalty and one out to subscription. Now, a pretty simple way to implement this would be just to have, run the first request, run the second request. So here the loyalty service award points. This is just some sort of syntactic wrapper over the top of whatever service call implementation we're using. We might be using gRPC here, or could be a wrapper on top of some REST calls. So what would normally happen in terms of how this would typically be implemented was that we would execute that first line of code, we would open the connection, we'd send the bits and bytes to loyalty, and then we'd wait for the response to come back, and then we would get that response object. And then this method would return. That response object would now have value, and then we would execute the next line of code. And then, which in turn would cause us to make the next call to the subscription service. So the first call is made, and once it's finished, we make the second call. Pretty straightforward. We can kind of see what's going on here. And honestly, in many situations, this is fine. And in some situations, you need to wait for one thing to finish before you do the next thing anyway. But in this particular situation, it might be needlessly wasteful when we're thinking about time and latency. Fundamentally, the problem with blocking calls is that, especially when you've got multiple calls happening in parallel, the latency of the operation is the sum of the calls. Because you have to do the first thing before you do the second thing, your latency ends up being the sum of all those parts. So if we said, for example, that the award points call took 50 milliseconds and upgrade subscription took 150 milliseconds, then the latency here is going to be at least 200 milliseconds in total for this operation. And of course, we have even more things to consider when we realize that latency isn't fixed. You will have variability, right? Typically, you look at latency in terms of a histogram. And when you've got multiple operations, each with their own distribution of latency, when you start summing them up, you often end up with an even wider distribution of overall latency, which in turn makes your system that little less predictable. When you get a lot of variability in throughput and performance, it becomes harder to understand if your system's operating correctly or not, which makes it a bit harder to manage. So actually having lots of these latencies added together is bad from a point of view of having a system that's speedy, but it's also can be difficult in terms of making a system predictable. So an obvious improvement here, and it's a pretty simple example, would be just to make these two calls happen in parallel. And this is a kind of common optimization that you would do anyway. And one of the easiest ways to do this would be to make those calls non-blocking. So rather than doing one call then the next, what we'd like to do is do them both at the same time. So in this example, what I've done is I've just used a reactive extension on the client side. So now within an enrollment, we're basically going to use a reactive extension to wrap the execution of each of those service calls. So here we've created a future. This is a bit of a syntactic wrapper. So a future is a read-only type, which the value of which will be defined at some point in the future. So effectively, when we create that future, the program flow would immediately return. We'd get that future back, but that future may not yet have fully had its value realized. So basically, you can think of the parameter of that future as having been packaged together and stuck into a background thread. That's probably what's happening behind the scenes. So you've now automatically got a thread behind the scenes that's making that connection out and talking to the loyalty service on our behalf. But the key thing is, from the point of view of this piece of client code, we would return almost immediately. And then we do the same thing for the second call. So this is great. So the call's now happening in the background execution. And so we would effectively end up with these calls happening in parallel, which is great. So that should hopefully bring our latency down, we would imagine, from in the areas of 200 milliseconds, maybe closer to 150 milliseconds, which could be a significant saving depending on what we're trying to achieve. The issue with this idea of non-blocking clients, though, is this idea that they're going to solve all problems, and non-blocking is the way forward. You should never block. You should never block. Non-blocking. You should not block. Blocking is for bad. Blocking is bad. But here's the reality. Sometimes you actually need the responses. I would argue most of the time you need the responses. So this idea that non-blocking is magically going to change the world starts to look a little bit shaky when we look at, even a simple example like this. At this point in the client program flow, at this point here, we don't actually know if those two calls have finished or not. They may not have. They may still be in flight. They may be blocked waiting for something else to occur. But at that point, in terms of the client flow, neither the award points call we cannot confirm that either of these calls have been made. And that's a problem if we want to confirm that and let somebody know this has happened, or if we want to then kick off some other processing once those things have occurred, or if we just actually need the responses from these things to kick off some other processing. So we have to wait for the results. So if we have to wait for the results, what do? We use an await or something like an await. And an await basically means block and wait until these things have completed. So we've got some non-blocking calls here, but we end up having to block anyway. Even if you have non-blocking calls, the logic of your processing may require waiting for things to happen. So you're still blocking and you're still waiting. So, just remember, it's not some sort of magical silver bullet. In general, though, non-blocking calls are a good thing to do when you can. Reactive extensions and the syntactic sugar around them can actually make your code much more, both more obvious and also more elegant. And I think it's a sensible thing to be doing, especially in situations where you're doing more orchestrated calls, where you're doing lots of downstream calls, finding a way to run them using non-blocking client codes. It still makes sense. So, okay, non-blocking is one thing, let's put that off to one side. So coming back to our Twitter thread, there were other responses coming in. This is Graham Lee, who's, you worked for many years at Tyro in Australia, which was a payments company and a bank. Knows microservices really, really well. And Graham Lee says, the definition I've been using is the sending service doesn't wait for completion of the receiving service before continuing and or completing its own work. So this is sort of this first part here is sort of talking about non-blocking, right? There's a bit of non-blocking stuff here. But going a bit further, Graham then says, but now that I think about it, Graham also expects temporal decoupling from the receiving services availability. So we've got some new words coming in here. We've got the terms temporal decoupling. That's a very fancy term. Now, as I mentioned earlier, the term asynchronous means different things, different people. Consistency means different things, different people. There are at least 3 different definitions that you can look at for what temporal decoupling actually means, but I'm going to talk about one specific type. Picking up this thread, Benjamin Johnson said, with synchronous communication for them, there's a direct communication between the sender and the receiver, but for asynchronous, there's an intermediary involved between the sender and receiver, for example, the message broker. And this is actually really picking up a theme that Graham had started, which is I've got some way of sending things to things that aren't there. And an intermediary is playing that role. So for them, for Graham and for Benjamin, they assume asynchronous communication actually means you've got an intermediary involved. So a classic example of an intermediary would be the message broker, some kind of place where you can store things before they get forwarded on, basically. So a classic example here would be, a message being sent from A to B. But rather than going directly to B, I actually instead give it to the broker, and it's the job of the broker to deliver to B once it becomes available. The thing to understand here, of course, is that B may or may not be available when I initially send the message. This is that temporal decoupling that Graham mentioned. So when you've got 2 services which are temporally coupled, if A and B were temporally coupled, B would have to be available when A sends its message. Whereas if I can temporally decouple them, in time, then I can send the message even if B isn't around right now. And you can imagine all kinds of situations where this could be useful. So here, though, the broker is going to keep hold of that message. And once B becomes available, it's going to receive that message and it can do its processing. This is a different type of asynchronicity. And we're sort of able to offload that guaranteed delivery to the broker itself. This idea of the message broker, almost like an inbox or a message box, was picked up by a couple of other people on this thread. So this particular respondent said, async is like dropping a snail mail in a red post box, then going on with your life. And then one day, boom, Postman Pat stuffs something into your house mailbox, along with millions of coupons and charity mailers. So for those of you not familiar with Postman Pat, this is Postman Pat, that's him, and that's his cat there. And this is the OG Postman Pat. Apparently there's a new Postman Pat that's CGI who drives in hovercrafts, but this is the original, right? It's still the best. But there is this idea that this almost like metaphor for message brokers as a mailbox. So I'm not talking directly, I'm putting something in a mailbox for you, you're picking it up afterwards. It's a very, very useful technical implementation detail, but also opens up some different interaction models as well. But you can also implement this, don't have to use message brokers, right? Lots of people basically use databases like message brokers. You probably shouldn't do that, but you can. File-based interaction between processes is probably still one of the most common distributed system integration patterns out there. But effectively using the file system like your intermediary. I'm dropping a file in a location, someone picks it up later on. It's, at one level, it is like a message broker. And you could also use email for programmatically communicating between services, but you really shouldn't do that. And I don't have to tell you why. But the key thing about this is we again have this idea that the client is a little bit more divorced from what the server is doing, which we sort of get with non-blocking, but this is taking it to a next level. I don't need to worry about whether or not the recipient of that message is available or not. However, of course, this does then shift our degree of trust to the intermediary itself. Is it good? Does it do what we expect it to do? Can it be relied on to not lose the message? So if we take the idea of request response and bring that into the world of, say, broker-based communication, we end up with a pretty straightforward interaction like this, which is service A sends a request. That request goes on the request queue for service B, and service B, when it's ready, receives that request. It does some processing. When that processing is complete, hopefully it has a response for us, and hopefully that's a positive response. And that response comes back on the response queue, and then we pick that up. So we've got temporal decoupling happening in both directions here. We're using the broker to offload that. Jobs are good. Right. Now, at this point, though, when I think we start moving into this particular world of looking at how brokers work and how consumers work, we're exposed to another problem here, which we didn't necessarily have with sort of the more straightforward non-blocking client code from before. Because in reality, right, we've got multiple instances of our microservices and multiple instances of both client, therefore, and server. So maybe we have two instances of service A, which is probably understating what we would actually have in real life. Normally 3 is a minimum, but we have service A sends a request, B downstream does the processing, sends back its response. There's no guarantee the response is going to come back to the same instance. Now, some people would see this as a massive problem. And then they would start saying, oh, no, I need a message broker that can guarantee that this gets routed back to the right instance of service A. That is the wrong way to think about this problem. That is something you absolutely want to avoid. Why do you want the response to go back to a specific instance of service A? That's because service A is in the middle of doing some processing and it needs to carry on doing that processing. So you're basically holding on to state inside this instance of A to carry on this particular piece of processing. Yes, that's what I'm doing. Okay, so now you've got the complexity of working out how to route the response back. In addition, how do you solve the problem of that instance dying? Okay, well, what we'll do is we'll take all that in-memory state and then we'll use some kind of replication of in-memory state between all the instances of A. It's like, oh yeah, now you've got another problem. Don't do that. Just implement your system so the response can go back to any instance of A and you'll be happier. It is simpler. It is much more likely to work. And in a failure mode, you're not going to worry about it. It's much easier to scale these systems as well, and you're not screwing around causing packet storms with replication of in-memory session state. And it also means you can use simpler brokers as well. I think in many ways, this model kind of forces us to think a little bit more about what happens when things fail. Now, I'm going to ask you a rhetorical question. If I was there in the room, I could get you to shout out numbers, but I'm not going to do that. So if I want to guess what the SLA is, what the guaranteed uptime is for a virtual machine on either Azure, GCP, or AWS. Right? What do we think? Hands up if you think it's more than 90%. A few of you, right? Hands up if you think it's more than 95%. No. Right, well, the number is, obviously, you kind of know where I'm going with this, because obviously I wouldn't ask this question unless the answer was shocking. The answer isn't 95% for a virtual machine or 90%, it is 0%. There is no guaranteed uptime for a virtual machine on any of the big cloud computing platforms. The SLAs you see are for the service as a whole. When they give you, say, I think it was 99.7% uptime for EC2, for example, they're saying we guarantee there'll be a 99.7% availability of the service to provision a virtual machine, not your specific virtual machine. You do not get an SLA for a particular machine, nor even an availability zone. That's why all the cloud vendors make it very clear you should be in more than one availability zone. That means if you're on a public cloud, you need to be designing with the assumption that you will lose nodes. And this makes it much more obvious that that's going to happen. And you just build an architect for it from the beginning and your life's a happy place. Screwing around with sticky session load balancing and routing of traffic is a fool's errand. But this then brings us back, thinking about node failure, then brings us back to thinking about what happens with our earlier non-blocking client code. How's that go? What happens there? In this environment here, this piece of code is running in an instance of the enrollment service. What happens if this client here, our consumer, dies partway through? What if we die here? What if we die at this point when the calls are gone, but we haven't done anything or processed the responses and our node dies? That could happen. Those points could have been awarded. That subscription could have been upgraded. That might already been done. So we now need to handle that situation. Now, I'm not going to go into detail about how you solve it, but I'll just say one quick thing. It involves retrying everything from the beginning. And to be able to retry things safely, you need to make these operations idempotent. But that is idempotency and retries is a conversation for another talk. But I do think that when you are forced into, when you're using intermediaries for communication between services, it does very much force you to realize the benefits of proper stateless processing. Not holding state in memory, offloading state if needed to databases and the like, makes your life so much simpler. Although there is no end of vendor-based products out there saying how they will magically solve your in-memory stateful processing problems, 99% of people do not need to do stateful processing. If you're one of the exceptions, you already know that. So we've got competing definitions out here, right? We've got some people thinking that synchronous versus asynchronous is about immediacy. Some people think it's about temporal coupling. Some people think it's about non-blocking. Some people think it's about having an intermediary or not. And it becomes very confusing. Like, which one of these is asynchronous communication? And of course, this then begs the question, well, does it actually matter? Because these competing definitions have been around for a very long time. Words have different meanings, and we are used to words having different meanings. This is a conference in Copenhagen. Many of you will be Danish speakers. All the Danish people I've ever met speak at least 2 languages, if not more. We are used to working in different languages, and even within one language that we might know, we accept that one word may have more than one meaning, and this is a world we're used to. So why is this a problem? Now, do you want to guess what word in the English language has the most dictionary meanings? Right. Again, I'd actually ask you the question if I was there in person, but let's be clear, right? I'll tell you the most then. It's set. So in the current official edition of the Oxford English Dictionary, which is the set of words, I think it's about 60 volumes, set has the most definitions. In the next edition, it's going to be coming out in 2037, I think. Run is going to have the most meanings. So at the moment, set has 430 different meanings in the dictionary. Run has 645 as of current estimations. Right, that's a lot of meanings. Do you know all 645? No. And the reality is we often don't need to know all of these meanings because we can often work it out based on context. We're used to doing this. We derive our understanding of a word from the context in which that word is placed. This is what I kind of learned from talking to Ian Cooper. When I was first talking to Ian about this presentation, it turns out, of course, Ian Cooper studied semiotics. And he said, oh, no, but what you've got to realize, Sam, is that the meaning of a word becomes more narrow as we add more words around it. By adding more words around a word, we get context and we get meaning. So let's think about the word run. Let's try this out as an exercise. I want you to think of the word run, and I want each of you individually to think, what does the word run mean to you? What's the first definition or the first meaning of the word run? Think about that in your head. I'm now going to put some words around it, and I want to see if my meaning matches yours. The issue got worse the moment the program was run. Was that the version of run you were thinking of? Maybe you thought of going for a jog. Let's try again. Think of a different definition of run. Now I'll put some more words around it. The economy crashed due to a run on the banks. Now, your thought, when you thought run, and I thought run, some of you might have been thinking of the same runs, but most of you probably weren't. But also, mine's valid. But I put the extra words around it, and the meaning of my run becomes clear. Whereas when I just say, what does this mean to you? And you're like, it could mean lots of things. What does this mean to you? The meaning is much more explicit. So we're used to this. Great. We have a word that has different meanings, and we deal with this well. So again, does it matter? Does this talk even matter? Does any of this even matter? I hope so, because I got up at 6 in the morning for this. The issue is that when we talk about synchronous or asynchronous is bad, synchronous is bad, asynchronous is better, we throw those terms around without sharing context. And that doesn't allow us to derive shared meaning when we're trying to have conversations and trying to think as an industry, what should we be doing? We are lazy, and we assume that when I use a word in isolation, that that word means the same thing to you as it does to me. Let's go back to definitions and meanings, by the way. I am poking fun a lot of the reactive manifesto, and I mean it with love because I don't agree with a lot of stuff in here, but I do agree with some of it. And there was a lot of hard work that went into this, but it also makes it very easy to poke fun. In the asynchronous section, again, the very beginning of that section, they say the Oxford English Dictionary defines asynchronous as not existing or occurring at the same time. And they're right, this is a definition of asynchronous. In fact, it's the definition of asynchronous you'll see from the Oxford Dictionary. If you Google, what does the Oxford Dictionary define asynchronous as? So if you Google it, this is the answer you get. But we've already learned that the Oxford Dictionary tracks lots of different meanings for asynchronous. In fact, if you actually have access to the Oxford English Dictionary, which anyone in the UK does for free, you can go to the library, and if you've got a library card, you can get it online for free as well. There are a lot of different definitions, and the Oxford Dictionary basically tells you where the term comes up and the context in which these terms come from. So we actually see that the definition that is most widely used, not synchronous, not existing or occurring at the same time, not coinciding in time, that is the definition that's basically used by the Reactive Manifesto, and the Oxford English Dictionary correctly points out that it was originally only ever used in medical contexts, this definition. And I don't think the Reactive Manifesto was in a medical context. There is actually a computing definition, by the way, of the word asynchronous in the Oxford English Dictionary. There's a section on computing in the Oxford English Dictionary that was not the definition used by the Reactive Manifesto or anybody else, in fact. You zoom all the way down to that section. It's only section 3. You don't have to scroll that far. And there's actually 2 definitions in there. But this is the one that's closest to what we do in terms of thinking about process communication. Designating data transmissions in which packets of data are sent at irregular intervals, with the start and end of each packet being marked by specific signals I don't know what this means. This makes sense when you're talking about defining a network protocol. It's at least closer to what we do. So using a different context, and in this context, this term absolutely makes sense. This is probably as close as we get to the original definition of what asynchronous means in the context of computing. But again, we don't tend to work at this level. We don't even tend to work directly with TCP anymore, right? So coming back to the meaning, value, what's the problem with all of these definitions? Fundamentally, the issue is this. Software is a type of socio-technical system. It's one of the best examples of a socio-technical system. Any software-based system is. So socio-technical seems like a very long word, but let's break it down and try and get into meaning. Socio basically meaning people, technical meaning technology, in the Greek sense of the word technology, meaning any sort of complicated system. So we often think of technology in terms of software, but technology has much broader terminology than that. And before you start thinking, oh God, this is kind of some lefty snowflake liberal view about how we're all going to get along as a planet, the term socio-technical systems was first developed actually in relation to coal mining in World War II. So this was actually a concept that predates computing by a long way, looking at the interaction between human beings and complex systems. And of course, getting those things wrong in coal mining can result in people dying. So this interplay is interesting. We're bringing people and technology together. We have to recognize that the amount of software created by individuals is vanishingly rare. This idea of the hero programmer sitting in their bedroom, writing a massive program by themselves that becomes impactful for the whole world, it's not true 99% of the time. Even when we think about someone like Linus, who created the kernel, the Linux kernel, actually what he did was get very good at accepting lots of different work from other people. Software is created by teams, by groups of people. To create good software, you need to be able to bring that technology together, you need to have good communication. You need to be able to work together to create software together. And when you've got two people trying to work together on the same problem, and they've got very different definitions for the same word, you're going to end up with an awful lot of confusion in terms of what we end up trying to build. And this is not a new idea. Some of you may be familiar, of course, with the Old Testament story of the Tower of Babel. This is believed to be basically, obviously, about the Babylonians. There are people of one language working together to create this glorious tower going up into the sky. And the Old Testament God saw the tower and thought, don't like that. I think you're getting ideas above your station. And the Old Testament God went down and changed the languages so that the people were no longer able to speak using the same language. Which is another example of the Old Testament God being not the nicest person in the world. It was like the New Testament, it was like a real, sort of character change, like almost like they've got new script writers in or something. He was much friendlier with the New Testament. Anyway, I digress. But the key thing was we have this very old allegorical tale of a massive project being undermined by language, by terms. People once speaking of one language, now speaking of many languages, and that undermined the ability of the project itself. This is not a new idea. And yet, time and time again, when having conversations about architecture and interactions and communication, we use the word asynchronous. It has so many meanings that it is effectively meaningless because we don't put the other words around it. So what can we do? What's the answer to this? I would stop talking about synchronous and asynchronous and talk about what does your application want? What behaviors does your application need to have? And then use more specific terms for what you want out of it. Describe how it should handle different situations. What should it do when a server is unreachable? How fast does your application need to be? What should you do if the client crashes? How should it handle that situation? And use those more explicit terms to define what you want out of your system and what you want from the interaction technology you pick. Say things like client should be non-blocking. Talk about wanting to run operations in parallel where possible. Say we're going to use a broker as an intermediary because we want these kinds of characteristics. I think it is important, though, when having these conversations is to get clarification. When people say things, and rather than assume you know what they mean, is to kind of ask them. And I've been guilty today of kind of using this talk to correct people about their use of the term asynchronous. I was talking endlessly about the reactive manifesto, for example, and things they get wrong there, which is a mean thing to do. In The Princess Bride, Vinegar says, this doesn't, you don't really know what this word means, do you? You're not using this word correctly. And of course, the joke in The Princess Bride is that we all know what inconceivable means, but Paul Vinegar doesn't. And actually, when it comes to the term asynchronous in the context of our projects, that isn't necessarily the case. There are lots of us that do have very different definitions of what this word means. So when someone says, oh, we should make this asynchronous or asynchronous is best, probably the best thing you can do in that situation to understand what they mean and to see whether or not you agree is maybe just simply to say, what does that mean to you? And use some more specific examples and questions to try and get that information out of them. Because, you might be surprised and find that you're talking about two completely different things. That's it. I'm done. Normally at this point, I would say, I'll enjoy seeing you around the rest of the event. I really hope you have a fantastic rest of the event. I hope the weather stays away. I'll gladly take all the rain over here in the UK because we could do some rain in our garden to keep you dry. But we have got about 10 minutes left if you've got any questions from anybody. But if not, I hope you have a great rest of the day.